So today we'll study derivatives. And well, a few words about the history. Initially, the derivative originated with Newton's attempt to study the velocity of falling objects. You may probably know Newton as a physicist, but he's also a great mathematician. And Newton realized that the problem of finding some change of values that are changing continuously, the rates of that, is similar to finding the slope of a line tangent to a curve. And that's what we will start with. So let's recall that if we have some straight line, let me just draw it here. So suppose we have some straight line that goes, say, like this. Then if you try to calculate the slope, remember that we'll denote slope by m. And suppose you have 2 points with coordinates x1 and y1, and say another point with coordinate x2 and y2. Then the slope of this line can be calculated by the following formula: y2 minus y1 divided by x2 minus x1. And you also can see it's kind of tangent. Okay, we'll discuss it slightly later. This is just the definition. I recall the definition that you probably have seen. But what is important part of this slope for the straight line? The point is that if you choose, say, another point somewhere here, for example, y3 and x3, the slope is the same if you calculate it using this point instead of these two. Say it is the same as y3 minus y1 divided by x3 minus x1. And in general, for other curves, it is not true. So for example, if we have some line that looks like this, so for example, here is my point x1, and y coordinate is y1. Where is it? Yeah, not nice. And say here is my x2, and here is my y2, and I say choose this point as a third point, x3, and y3. Then you can see that you will check, basically, if you have the equation of the slope, that m1 that can be calculated using, say, first 2 points, y2 minus y1 divided by x2 minus x1, will not be the same as m2 that calculated using second 2 points, say y3 minus y2 divided by x3 and x2. So let's call it, say, point P, Q, and Q tilde. So you see that the slope is changing, and it's not even the same as, say, M3 when you choose first and the last one, y3 minus y1 divided by x3 minus x1. So all these three slopes that you can try to calculate are different, and you can see that the slope is changing when you change the points on your curve. But there is And no. And we can think about the just a moment. We can think about the following chords. Say chord PQ. Just a moment. PQ, and then straight enough. It should be straight line connecting P and Q. And this chord, it's a straight line, so we can calculate its slope, and it turns out that that will be our M1. And of course, from the picture again, you can see that the slope of the another straight line, which connects Q and Q tilde, which is here, that will correspond to M2, because I'm using Y3 and Y2 and X3 and X2. So even from the picture, we can see that the slope is different. One is steeper than another. So the slope is changing, but there is specific line, which is also straight, that can be assigned to the specific point. And this is called a tangent line. Say tangent line that goes through the point P is the line that touches our curve only at point P. Let's call it T. Yeah. So T corresponds to the what is called tangent line. And this tangent line is the limit of the chords. So how to find this tangent line? So we see that if we let point Q approach our point P, what will happen with the with our chord? It will approximate our tangent line, right? So if I have, say, I start with Q tilde, then my chord is, let me do another picture. So it will be better probably. So I have this point P, and now I'm starting approximate my chord, my tangent line by chords. So this is my first chord. Then I allow Q becoming closer to P. Say Q, this is Q0, this is Q1. Then my chord will look like this. Then it's, let's put it here, Q2, and it will be like this, and so on. And in the limit, when Q will be very close to P, I will get something that looks like a tangent line. And that's how you can, this is the definition of the tangent line. So T is a limit of the line PQ when Q goes to P. Okay. Of course, it's not very useful. I mean, this is just how you can define it in geometric way. But what is interesting is how to find the tangent line, the slope of the tangent line. So let's do that. Again, let me draw one new picture. This is my P, this is my Q. And let's calculate the slope of our chord one more time. So say we have this chord PQ. And let me draw this following triangle, this right triangle. And so P has coordinates, say x0, and this is y0. And Q will have coordinates x0 plus some delta x. And this delta x is just a change in x. We can call it this x2, but for some reasons, it's better to consider this point as x0 plus x0 plus some delta x. And we can say that x plus delta x is called, we can say that x has been given an increment delta x. Sometimes delta x is called also increment. So what we can say from the picture, we can see that delta x is just the side of this triangle, right? Because initially I have x0, then I'm adding delta x, and then I obtain x2, which is x is not plus delta x. And the same story happens with y. So initially I have y0, and then I'll obtain y2, which is I will also trying to say this is my y2 that I will think as y0 plus some delta y. And again, delta y is just the side of this triangle PQ, and let's call this, say, I don't know, L, point L. Okay, so what we can see? We can see that, again, the slope of our PQ. So again, what is the slope? It is x2 minus x0 divided by y2 minus y, sorry, other way around. It is y2 minus y0 divided by x2 minus x0, right? But what is y2? We decided that y2 is the same as y0 plus some delta y. And then I have minus delta 0, delta y naught, sorry, and divided by x2, which is again x naught plus delta x minus x naught. Correct? This is the slope of the chord PQ. Pardon. Q, nevertheless. And what I can see that there are some cancellations, because if I open the parentheses, I will see that y naught is cancelled by another y naught, the same for x0. And finally, I get that my m is equal to delta y divided by delta x. So in some sense, we have our triangle PQL, and if you want to find the slope for the chord PQ, it's just one side delta y divided by another side delta q. Okay, this is kind of important step. To remember. But then what we have? We have that what is y2? Y2 is actually, so suppose our curve is described by a function f of x. Then we can calculate what is the value of y2. Y2 is the value of our function at point x2, right? But our x2 is what? It is f of x naught plus delta x. Correct? And what is delta y? Again, delta y so we have seen that delta y is, okay, better to write it in the following way. We have that y2 is y0, y0 plus delta y. So delta y thus will be y2 minus y0. But y2 is f of x naught plus delta x, and the same we can say about y0, because y0 is f evaluated at x naught. So instead of y0, I'm plugging here f of x naught. And so my slope, finally, slope of PQ, which is m, can be calculated in the following form. So we derive that it is delta y divided by delta x, but we see that delta y is the same as f of x naught plus delta x minus f of x naught divided by delta x. Okay, so this is second important step. And now, so we found some description for our slope in terms of formula. And now we are ready to calculate the slope of our tangent line, because again, what is slope of t, where t is a tangent line? Oh, better to start with again with the t. T is a limit of the line PQ when Q approaches to P. It's not rational numbers, just Q. But what is the coordinates of Q? So our Q is this point that has coordinates x plus delta x and coordinates y naught plus delta y. So you can say that Q approach to P is the same. So you can say that it is the same as that the coordinates of these 2 points, coordinates of Q approach the coordinates of P. So coordinates of Q are x naught plus delta x, and and the y coordinate is y naught plus delta y, and it approaches the coordinates of P, which is x naught and y naught. So we can see the same as delta. As a corollary, we can see that the statement that Q approaches to P is the same as delta Q goes to 0. Delta, sorry, by delta Q, delta X. Because when delta X goes to 0, then indeed X0 goes to X0, X naught, and delta Y also goes to Y naught. And so we can say that the slope of M, slope of T, what's happened with me, is the same as limit of the slope of PQ when, again, P approaches to Q, Q approaches to P. Doesn't really matter. But we calculated the slope for PQ. It is this. And I just rewrite it here. F of X naught plus delta X minus F of X naught divided by delta X. And as we discussed, the condition Q goes to P is the same as delta X goes to 0. So instead of writing Q goes to P, I will write down delta X goes to 0. So yes, and this is the formula for the slope of tangent line. At point P that has coordinates x0, x0, y0. Okay, and here are some notations. So we can write this limit delta y divided by delta x. When delta x goes to 0, sometimes it's denoted by dy over dx. Sometimes it is denoted as f prime at point x0 if we specify the initial point. Sometimes it's also denoted by d f of x divided by dx if we have that y is a function is f of x. Or you can see notations like this, d over dx applied to f of x, or it is the same as dx, capital D, x f of x. And all of this expression are called derivative of f. At a point x naught. And as we discussed last time, sometimes the limit can be calculated, sometimes it's not defined, sometimes there is no limit. And also, you can probably see that you had some problems in homework that where you have to calculate the function at the point x plus delta x. And this will be helpful when we will calculate the derivatives of some functions. Okay, so as a summary, we see that the slope of tangent line at point x naught is just the derivative tangent line, slope of the tangent line to the curve. Tangent line at point x0 is just the derivative dy over dx, which is the notation for the following limit. Delta x goes to 0, delta y over delta x. And this is kind of the, oh, now I need take root, the region of the derivatives. It is the slope of the tangent line. Okay. F of x naught, I just rewrite what we have found, divided by delta x. So this is the main result of the section 2.3. The slope of the tangent line is the same. If you have a curve y equals f of x, then you can find the slope of tangent line by calculating the corresponding limit, which is called the derivative of the function. Let's start section 2.4. It just, again, it is the same as the derivative by the four-step process, but it's just how to calculate the derivatives of some functions. So again, let me write the derivative of x. So suppose yeah, I forgot to mention that if such limit exists, if the limit delta x goes to 0, f of x naught plus delta x minus f of x naught divided by delta x exists, then f of x is called differentiable at point x naught, yes, differentiable at x naught, and if it exists at every point in AB, in the interval AB, then f of x is differentiable in the whole interval. If the same stuff, but at every point in AB, interval AB, then the function is differentiable in the whole interval AB. And so the process of finding f prime of x is called differentiation. Differentiation. And the rest of the section will do this process. So again, there is a four-step process in a textbook how to find the derivative. Actually, I don't understand why it should be four-step process, so I will do three-step process. But if you like 4 steps, you can look at the book. The 3 step process. So the first one, so suppose you have your function y equals f of x, and first step is to calculate delta y. As we figured out, delta y is the same as f of x naught plus delta x minus f of x naught. That's what we did in the previous sections when we evaluated functions at some specific points. And second one, write down the ratio delta y over delta x. Basically, just write it. You don't need to do anything. On the first step, you have to indeed substitute x naught plus delta x into your function and calculate something, while the second step is just rewriting your result. And let me erase x naught, just x. It's just the point of notation. So now we are calculating the derivative at point x, not x naught, but it's now not very important. Plus delta x minus f of x divided by delta x. So, and the most important part is the third step. Calculate the derivative of our function, and in order to do that, you need to consider the following limits. When delta x goes to 0, delta y over delta x, which is f of x plus delta x minus f of x divided by delta x. So maybe it looks complicated, but once you get used to that, it will not be a big deal. So let's do a few examples. So consider the function y equals 1 minus x squared. So first, let's calculate delta y. So first step is to calculating delta y. So it's f of x plus delta x minus f of x. So f of x plus delta x, again, this is kind of the first step in the textbook. Let me do it separately once. It is 1 minus, and instead of x, I'm plugging x plus delta x squared. So it is 1 minus x squared. Okay, let me do it more precisely. So it's x squared minus 2x delta x and 2x times delta x and plus delta x squared. And if I open the parentheses, I will get 1 minus x squared plus 2x times delta x, and my plus here should be minus, and minus delta x squared. And so my delta y, okay, I'll do like this. My delta y will be 1 minus x squared minus 2x delta x minus delta x squared. This is the first part. And the second is f of x itself, which is 1 minus x squared. And you can see that there are some cancellations, like 1 and x squared. And you're left with the following. It is minus 2x delta x minus delta x squared. And this is the end of the first step. It's quite long, but straightforward. And the second step is to write down delta y over delta x, which is the same as f of x plus delta x minus f of x divided by delta x. And this is that what we calculated on the top. It is minus 2x delta x minus delta x squared, and divide by delta x. And again, I see that delta x is a common factor, and I can divide term by term and get that it is minus 2x. Okay, maybe it's again better to write it down like this. Delta x times minus 2x minus delta x, and divide by delta x. So I have cancellation here. And the final answer is minus 2x minus delta x. So the second step is to write down the ratio and try to simplify it as much as possible. And the third step is to consider the limit of delta y divided by delta x when delta x goes to 0. So in our case, we get that it is the limit when delta x goes to 0 minus 2x minus delta x. But x doesn't depend on delta x, while so I can write down that it is minus 2x, because in some sense it's a constant for this limit, and I get limit delta x goes to 0 of delta x. But this is, of course, just 0. And so the final answer is minus 2x. So we get that the derivative, so I can write down it's like that, 1 minus x squared prime, notation for the derivative, is equal to minus 2x. Doesn't want to work. Okay, slightly more complicated one. 2x cubed minus x. So again, first step is to calculating delta y, f of x plus delta x minus f of x, which is the same as 2 times x plus delta x cube minus x plus delta x. This is my f of x plus delta x minus f of x, which is 2x cubed minus x. And again, if I expand the cube power, I'll get 2x cubed plus 3x square delta x plus 3x delta x times delta x squared plus delta x cubed minus x minus delta x. and then minus 2x cubed plus x. Long expression. Let's be careful with that. So I get 2x cubed plus 6x squared delta x plus 6x delta x squared plus 2 delta x cubed minus x minus delta x minus 2x cubed and plus x. And again, I see some cancellations. For example, 2x cubed and 2x cubed and x and x. and also I can combine the terms. So in general, it's also the good step to combine your expression in powers of delta x. So I have delta x times 6x squared from this term, and I have delta x here. So it is minus 1. Then I have delta x squared times 6x, and I have delta x cubed times 2. So this is my first step. Second step is delta y over delta x. So it's my expression that I found on the previous step. And now I divide by delta x. So again, delta x is a common factor. And what I get, I get 6x squared minus 1. This is kind of first term. Second term is multiplied by delta x times 6x. And I have delta x squared times 2. And the last step is the limit of this expression when delta x goes to 0. It is the same as this limit. 6x squared minus 1 plus delta x times 6x plus delta x squared times 2. But again, we see that first term doesn't contain delta x, while second one does. And by the, we remember that limit of the product of two functions is the same as the limit of first function times the limit of the second function if these two limits exist. And since the limit of the first function, which is delta x, is 0, we get that the whole expression goes to 0. And the same for delta x squared. Both of them goes to 0 because they contain delta x that goes to 0. And finally, we get that derivative of our initial function, 2x cubed minus x. Let me write down this time like this, d over dx is equal to 6x squared minus 1. Again, this is just another notation for the derivative. I write it down in this way, so you will be familiar with it. Okay, any questions about this example? So what is the difference between this example and the previous one? In this case, we see that we can get not only first power of delta x as in the first example, but also we can get delta x squared, delta x cubed, but in fact it doesn't matter, because if you see something that contains delta x and it's in the numerator, that means that it will go to 0. And what I also wanted to mention that in these two examples, we see that there are some cancellations when we consider delta y, and this is kind of general general rule that when you consider delta y, you will in fact have some cancellations. If you do not have, that means that you should check yourself, because it should be. Unless it's not a complicated function, like a trigonometric function that we will study later, or logarithmic function, and there you have to work harder. Okay, let's do another example. Or, for example, a rational function, because it will be also difficult. And so let's do this example, 1 over x minus 1. And we want to find the derivative y prime at point, say, 2. So to calculate y prime at point 2, we first need to find just the derivative of our function and then evaluate it at point 2. So again, let's consider our 3 steps. First, delta y, which is again f of x plus delta x minus f of x. And so I get 1 over x plus delta x, I substituted, minus 1, and minus 1 x minus 1. So, and here is a problem because there is no nice cancellations. But what we can do, we can use the common denominator technique. So we have 2 fractions, and I want to write it down as 1 fraction with the common denominator. So that means that I need to multiply second by the first denominator, and the first one by the second denominator. So what I'm doing, I have this, and I multiply and divide by x minus 1. And the second, I have this, and I multiply and divide by this expression. So I multiply by one actually, but now why it's important that I have the same stuff in the denominator. And when I have the same denominator, I can add and subtract fractions. That's what I will do. So I have x minus 1 from the first, and I have minus the stuff that comes from the second one, x plus delta x minus 1, and divided by x plus delta x minus 1 times x minus 1. And now we see the cancellations because we have x and minus minus 1, which is 1, that cancels minus 1 here. So I get that it is delta x divided by x plus delta x minus 1, x minus 1, with minus sign, because it was in front of the parentheses. Okay, any questions? So that was our first step. Second step is just divide by delta x, and in this case it is very easy. So we have this x plus delta x minus 1, x minus 1, and I divide by delta x, so there is extra delta x here. And again, there is cancellation. So I get that is minus 1 over x plus delta x minus 1, x minus 1. And the final step is this limit. Which is the same as this limit, minus 1 over x plus delta x minus 1, x minus 1. And again, here I'm using the properties of the limits. First, I use that limit of the function of the ratio of two functions is the same as the ratio of two functions. If some conditions are satisfied such that both limits exist and the limit of the denominator is not zero. So I can rewrite it as a limit of -1. I will skip delta x because it will help save the place. And I have this x minus 1. And now again, I can use the rule of the product. So I have two functions in the denominator, and this is the same as the product of the limits. Limit of the second one is just x minus 1 itself, while the limit of the first one, we see that delta x goes to 0. So I just eliminate it. So I get it is the final answer that it is -1 over x minus 1 times x minus 1, which is -1 over x minus 1 squared. So I get that derivative of f1 over x minus 1 is -1 over x minus 1 squared. And the last step, because initial question was to find the derivative at the specific point, at point 2. So my y prime is the same as f. My y prime at point 2 is the same as derivative of my function. Point 2 is just -1, and I substitute x equals to 2 minus 1 squared, which is -1. Okay, so this example is slightly more complicated because we do not have cancellations at the beginning. We had to work a little bit to consider the common denominator of two fractions, and only after that we see some cancellations. But after we do that, the rest it was quite straightforward. Another example when you will not have cancellations at the first step is when you have some irrationality, like f of x is square root of x plus 2. And we want to calculate the derivative of this function. Okay, so again, let's consider delta y, which is f of x plus delta x minus f of x. And again, it is square root of x plus delta x plus 2 minus square root of x plus 2. So again, we cannot cancel something because there is no such rule for the square roots, but that's fine. Let's go further and write down delta y over delta x. That will be this. Divided by delta x. And now the third step is to consider the limit. So the limit when delta x goes to 0, square root of x plus delta x plus 2 minus square root of x plus 2 divided by delta x. And here is another important remark. You cannot plug delta x equals 0. So you have seen that sometimes when you're calculating the limit, you can just substitute the value of x or delta x when it approaches that, and you'll get the answer. But in this case, if you try to do that, what you'll get square root of x plus 2 minus, okay, plus 0, but I skipped that, minus square root of x plus 2 divided by 0. So you get something like 0 divided by 0 in determinant form. And it will happen in all cases when you try to calculate the derivative. If you just plug delta x equals 0, you will get 0 divided by 0. And so you have to use some tricks that we discussed during our section 2.2. And one of the tricks was to multiply by the conjugate expression. So this this is the same as, so I want to get rid of irrationality, so I multiply and divide by the following function: square root of x plus delta x plus 2 plus square root of x plus 2. And I divide by the same, so initially I have delta x, and also I divide by the same expression, delta x plus 2 plus square root of x plus 2. Yeah, and here's another comment that I have seen in your homework. Common mistake is the following, that you write down here equality while it cannot be equality because there is no limit. So either you just consider this expression separately and write it down, or if you want to write equality, so you write limit of something is equal to, still continue writing limit, delta x goes to 0. Without limit, expression like this, it's not equal. So here is the limit when delta x goes to 0. Sometimes you can skip these limits, the what is the limit of delta x, when you write it many times, and it's understandable, and only write it at the end of your expression, but you should still write the limit sign. Okay, then again, in this expression that I obtained, I see that there is a formula for the difference of squares. So I get that it's the same as the limit delta x goes to 0. So I have first squared, which is x plus delta x plus 2 minus x plus 2. And I have delta x, and I have x plus delta x plus 2, and I have plus x plus 2. So I get this one, right? Because that's what we discussed last time. This is a minus b times a plus b is equal to a square minus b square. And now I see some cancellations. So x cancels x, 2 and 2. So I get this is the same as, and yes, I get that it is the same as limit delta x divided by delta x, square root of x plus delta x plus 2 plus square root of x plus 2 when delta x goes to 0. And again, I see cancellation of the delta x. And what is left? Again, the same story. I have the limit of the fraction. It is the same as the fraction of the limits. In the numerator, I have just 1. In the denominator, this term doesn't depend on delta x, while this will give me that delta x goes to 0, and I'll obtain square root of x plus 2 again. So what I'm saying that finally you'll get that it is 1 over square root of x plus 2 plus square root of x plus 2. Here I can write anything without limit because I already calculated that. And finally it's 1/2 times 1 over square root of x plus 2. So we get its derivative, how I wrote it, d over dx of square root of x plus 1 is 1/2, I can write down it like that, x plus 2. So we have found that, say, if we have function 1 over x minus 1, then its derivative will be minus 1 over x minus 1 squared, and we calculated that the derivative at point 2 is minus 1. That's what we found. But we can again come back and interpret it in the following way, that the slope of the tangent line at the given point, at point x equals 2, is minus 1. So how we can see it on the picture? So the function y equals 1 over x minus 1 is a hyperbola shifted by 1 to the right. So it is 1 here, and it looks like this. And so it has asymptotes. This is y equals 1 over x minus 1. And at point 2, our tangent line will have slope minus 1. So that means that if I draw the slope, the straight line, then it will have slope minus 1. So it will go like that. And in fact, when we know that this straight line goes through the point, the specific point, so as we discussed, the tangent line touches the curve at that point, and also we calculated the slope of this straight line. And that means that we can find the equation of this line, in fact. Because what we discussed that for the straight line m, which is y minus y naught divided by x minus x naught, is constant, right? And tangent line is straight line, and so what we calculated that in our case m is equal to minus 1, and we know that our tangent line touches that the tangent line touches our curve at point x equals 2. That means, so at x equals 2, our function has value, so our function is x minus 1, then our function has value 1 over 2 minus 1, which is 1. So that means if the tangent line touches that curve, that means that tangent line goes through this point with coordinates 2 and 1. Right, so again, we have that the slope is minus 1, and it goes through the point 2, 1. So we can substitute that into our definition of the slope. This is x naught, this is y naught, and get that minus 1 is equal to y minus 1 divided by x minus 2. And if you multiply both sides by x minus 2, you will get that y minus 1 is equal to minus 1 times x minus 2. Or if you like, you can write it in the following way, that it is 1 plus 1 minus x plus 2, which is, what it is? It is 3 minus x. So the equation of our line is 3 minus x. So there are different ways to write down the equation for the straight line. Either it is in this way, kx plus b, where k is slope and b is some constant. Or if you know that the line passes through the specific point, then you can write down that it is y minus y naught is equal to k. Okay, let's call it m, because we called slope m. M times x minus x naught. So we started with the tangent line, and we can go back and calculate the equation of the tangent line once we calculated the derivative of our function. Okay, I think that's it for today.